Alright. Hey team, I think I'm live, so can you just quickly confirm to me by typing in if you can hear me? That'd be awesome. Thank you so much. And if you can't hear me, let me know, and I will try to fix it. Awesome. Alright, so today we've got a few things to cover that I want to talk about. So I first off want to talk about chain rule, and Leibniz notation. Okay, perfect. Oh, thanks, guys. Yeah, I was freaking out. My computer came up with some weird error message, and I was worried. So, chain rule and Leibniz notation. I could do them separately, but I'm going to do them together. So first off, before we talk about chain rule, we're going to talk about Leibniz notation. Okay. So first off, we have function notation. This is very common with Newton. We have graphical notation, so y, x, Cartesian like sort of situation. But I prefer this function notation because you can find out things. So if I said y equals x squared, then I said, what is f of 3? Then you can comfortably tell me that that's 3 squared because you replaced x with 3 and you've got 9. So functional notation is really useful in this way. And so similarly, if I asked you what f dash, if I asked you what f dash of 3 was, well, first off, you'd work out what f dashed is, and that would be 2x. And then you'd go, oh, okay, so it's 2 times 3, which is 6. So this notation is spectacular for this kind of operation. So Newton's notation, really awesome. But what we're going to do is we're going to move into some new notation. So new notation. So you may have used it last year, but I want to start off again with it. Okay. So y is a function. dy by dx is its derivative. So f of x, this is f dashed of x. Okay, that's first derivative. Okay, and the thing that's really important and key here is this notation. It is d by dx. And I'm going to show you how we read this. The derivative with respect to x. Derivative with respect to x. That's how you read that. And so dy by dx is the derivative of y with respect to x. And that's the operator, the d over dx. Is the change in y, so change in y, so small d, small delta of y over the small d delta of x. Yes, but the black notation is the derivative notation. And that's really important. And so when I write this, the y is the function. So sometimes you might see this written as d over dx of y, because it's a little clearer that way. Okay? You're like, okay, let's do some interesting things. So find d by dx of x squared. Differentiate with respect to x that function. It's 2x. This is called the differentiation operator. It's a really awesome way of doing things. And so this is the way I prefer to use it. Okay? You're like, okay, Mr. Dharma, that's really cool. Why does that matter? Well, if I then go back to our notation from before, we had f of x, f dashed of x. If I want to differentiate again, I get f double dashed of x, or double prime, f triple prime of x. And if I kept going, the number of dashes I'd have to put in would have to increase. And in fact, after 3, you end up putting in brackets up the top the number of times you've differentiated it. But it's weird because it's not the power of. And so the notation gets messy. Okay, so that notation is good, but it gets messy. Let's try what this notation is. So if y, the derivative is dy by dx, the derivative is d squared y over dx squared. And I'm going to try and explain that soon to you. And then the third derivative is d cubed y over dx cubed, and so on until you get dny over dxn. And the notion here is that you're doing this. It is dy by dx of d of dx of dy by dx. And do you notice that there's 1, 2 d's, so that's why it's d squared, and there's 1, 2 dx's, and there's still just y, the second derivative of y. And that's why that notation is that way. I don't want you to split the d and the x up, because this dx is just awkward notation. They're not separate letters. It is change in x, and that's the unit there. But that's how that comes out. So if ever you see of y, that is the same as the third derivative of that, also the same as 1, 2, 3 of that, if y equals f of x. Right? I think that's pretty cool. Right? The d, that's why it's d squared y over dx squared, because it's not, you won't put the squared on the y. Guys, can you just comment to see if you can still hear me? Because I keep getting messages that my audio keeps cutting out, but I don't think so. Alright, and so this notation is really powerful. So let's try a couple of questions. If y equals x squared plus 7x, find dy by dx and d squared y over dx squared. Okay, Jackson, I'm assuming that yup is to signify that you can hear me. Perfect, outstanding. All right, cool. So let's try dy by dx, differentiate y with respect to x. So here, multiply by the power, take 1 off the power, plus multiply by the power, take 1 off the power. And then the second derivative here is differentiate this. Quite nice, quite simple, quite elegant. And this notation now becomes very, very powerful for us. We can use it in multiple ways, but I want to show you some weirder ways we can use it. Okay, so we will soon parametric differentiation. But we'll learn this in a little while. I'm going to just cover a few things about chain rule. So let's go. Let's talk about a chain rule. Suppose y equals u squared, and u is equal to 2x plus 7. Right? So far, we can do some pretty cool stuff. So we could substitute. We could do y equals by the derivative of the inside, which is 2, and so my answer is 4 times 2x plus 7. Right, that's really cool. It's a very simple problem. Nothing crazy about it. But let's show you something wilder and weirder that we could have done that could make this a little bit awesome. What I'm going to say is, to find this, I can do something weird and wonderful. To find dy by dy with respect to u, I can differentiate y with respect to u. And I can differentiate u with respect to x. And this is the glory of the chain rule. If I have a function nested within a function, nested within a function, however I want to do it, as long as I cause a chain reaction that causes all of the other terms to cancel out and me being left with dy by dx, I can do that without doing any crazy maths. So let's try. So here goes. Dy by dx is equal to dy by du. What is dy by du? Well, what's the derivative of this? That is just 2u. And what is the derivative of this? Just 2. So my answer is 4u. U, that is my answer. Same as what I got before. But something greater happens, because look at what happens if I nest it some more. Try y is equal to u to the power of 3. U is equal to w squared plus 7w, right? And if I then said w is equal to 5x squared, okay, it looks crazy. And if I were to substitute, it's going to get messy. Shall we do it? Yes. Okay. This is what substitution will do. Right? So first off, we're going to sub this w into here. So we get u equals 5 thing that squared plus 7 times that thing. Okay. It's not terrible just yet. But then this cubed. That already starts to look pretty ugly. And so if I ask you to differentiate that with respect to x, you could, but it'd be a bit ugly. But let's try the other way. So I know that I want dy by dx. But what can I do? I can find dy by du. What can I do to get u? I can find du over dw. or differentiate u with respect to w, and I can differentiate w with respect to x. And if you can see this chain, the u's cancel, the w's cancel, the chain closes up, and now I have a function that differentiates. By just doing 3 simple derivatives, I can get dy by dx without this horrible substitution. So shall we try it? Okay, so here goes. Dy by du, 3u squared. Du by dw, 2w plus 7. Now, dw by dx, that is 10x. In all honesty, that is a lot prettier as an answer. If I now so want to, I could substitute x into here, I could substitute w into here, and then substitute x into this function. But there is no need for me to have a function solely in x, because I now have the derivative dy by dx in terms of uv and uw and x, and it's okay, it works, it's correct. And I think that's outstanding. So the chain allows me to not have to worry about resubstituting some nasty looking functions, as long as I've got a plan of attack as to how to look at them. So with Leibniz notation, we get a prettier view of how to do some math questions. I can substitute the x into here. I don't need to, and I know what my answer is. And that's pretty awesome. And I might, might want to substitute, might not want to. But that's up to me. And sometimes if I know that x is 7, suppose x is 1. If x is 1, then w is equal to 5 times 1 squared, which is 5. And then u is equal to, what was my function for u? Is equal to w squared plus 7w. So that's 1 squared plus 7 times 1. No, sorry. W squared plus 7w. So that's w is 5. And so now I have 25 plus 35, that is 60. Without having to substitute x back in, I can just go dy by dx at x equals 1 is equal to, let's go, 3 times 60 squared plus 2 times 5 plus 7 plus 10 times 1. And in all honesty, that's a lot prettier than substituting horribly through. Okay? Now that is why chain rule is so powerful. And so this is why I didn't want to teach it to you the other day in such a annoyingly simplified version. Because the chain rule is not about, just differentiating with respect to x, but it's using parts of differentiation carefully so that you don't have to substitute outrageously. And this is really useful to you when you're doing application questions, when you've got ideas such as volume, surface area, and stuff like that, where some parts you don't necessarily need to substitute, and you want to just look at things in their own kind of way. Can we do some more examples of that? Yes, of course we can. I think, let's try this. I'm going to leave this for you to try. Okay, but this time I'm going to make the functions a little bit more interesting. I'll make sine of u is equal to w squared plus 4w. And then let's make w is equal to e to the x. All right. And question is, find dy by dx when x is equal to 0. Go. Okay. Why do I plus those terms? Isn't there a period so I times? I will times, yes. Harry? I will eventually times this, but I can't be bothered timesing 60 squared times 3, whatever, 17, 10. This is going to be 60 times 60 is 3,600. 3,600 times 3 is 36 times 3 is 108, 108, 10,800, 10,800 times 10 is 108,000, 108,000 times 17. I don't know what that is, right? And Mustafa, no, you're not slow. This is wildly weird, but I just thought we'd do it, right? So find what dy by dx is when x is 0. You could, first option, plug in e to the x into each of these and then try to differentiate that monstrosity of a function. Or you could find a way to differentiate and find dy by dx, and I think you'll see which one's nicer. Yep. Sorry guys, there's about a 40-second lag between your asking a question and my answering, and so I've got to wait to see your question and then answer it. So it adds up. Okay. So let's give this a go. What I'm going to do first is the wrong way, just to show you how ugly this is. So I'm going to write u in terms of x. It's going to be e to the x squared plus 4e to the x. And then I'm going to go y equals sine of e to the x squared plus 4e to the x. It's not terrible, but it's not pretty. So I could differentiate that. Or I could notice that to get dy by dx, I can go dy by du. Then I could do du by dw. And I could do dw by dx. And multiply them together. And these things cancel. The chain, it's a chain reaction. The chain rule is implemented. And so, if I just continue it over here, I get dy over dx is equal to dy over du. What is dy over du? Okay, that is cosine u. What is the derivative of this? 2w plus 4. What is the derivative of this? E to the x. Now, all I need to do is now plug in x equals 1. So if x equals 1, w is equal to e to the 1, which is e. Okay? So e is a number. No, I didn't say x equals 1. I said x equals 0. Sorry, let me do that whole section again. X equals 0, rather. And so then w is equal to e to the 0, which is 1. Okay, that's really nice. And so then if w is 1, what's u? U is equal to 1 squared plus 4 times 1. So u is equal to 5. And so then, do I need to work out what y is? No, I don't. 1, 2, 3 numbers. Let's substitute them in. So dy by dx is equal to cosine 5 times 2 times 1 plus 4 times e to the x, e to the 0. Let's figure out what this is. Cos 5. 2 times 1 is 4. 2 times 1 is 2, plus 4 is 6, and then e to the is 1. And so I've got 6 cosine 5 as my answer. And I promise you, that's a lot nicer than trying to do, any long division, or not long division, any long differentiation of this by trying to hold ideas in your head. Sorry guys, I'm just going to mute my mic for a second whilst I cough. So I hope that maybe with a little practice you can see why something like this would be really useful. Will there be lots of questions like this? I can't promise you, but I'm here to teach you some real cool ideas, and I think the chain rule is awesome. Oh no, sir. Oh no, it's fine. So I think that's all I want today. Yeah, I've been washing my hands, team. Also, who's excited about being back at school on Monday? That's really exciting for me. Okay, so I think that's the chain rule covered. I think that's the Leibniz notation and why that's useful covered. I'm going to just wait 2 minutes, see if any of you have any questions. And if not, I'm going to just end the video there. I think we've covered a lot. Try to give yourself some questions of some functions that look like this and see if you can do it, and see why using the chain rule is so beneficial, because it simplifies the work. Alright, give you a couple of minutes to ask me questions, and otherwise I'll just end the call. Alright, team. Not sure anyone's yet asked me a question, but thank you for coming along. I'll do another stream hopefully on Thursday, but just watch this space. I might not. Depends on what's happening at school. But thank you for coming along, and hopefully that was beneficial for you. All right. Thanks, team. Catch you later.